Hi, my name is Justin Norris, and I am currently a student at Southern Methodist University, where I am involved in the Master of Liberal Studies program, and am currently concentrating in environmental sustainability. While there, it's given me the opportunity to think deeply about many of the most prescient environmental problems that we face today. The problem that has garnered most of my attention, because of its existential nature, is the threat of climate change caused by the imbalance of the carbon cycle. One of the most promising, albeit partial solutions, seems to be, in my opinion, the use of biochar enhanced compost in order to sequester carbon and rebalance the cycle using our soil. The rapid increase in atmospheric carbon is endangering the relative stability of Earth's climate. The carbon cycle represents the terrestrial exchange of carbon between incredibly complex systems, and is simply and quantifiably imbalanced. The average CO2 in the air is now above 400 parts per million. This is a full 100 parts per million above anything humanity has ever seen. The physical danger of the warming effects from the atmospheric carbon is already evident. An increase in storms and drought conditions, but climate scientists predict that the situation will get much worse as carbon levels increase. The degree to which humanity manages our part in this cycle will determine just how much damage we sustain in the coming centuries. One key to this management is the immense amount of carbon that is woven into plants, which they require for respiration in the form of CO2. Atmospheric carbon provides the building blocks that give plants the strength that they need through varying amounts of a substance called lignocellulosic structures, or a woody material. This material will retain the carbon for as long as the plant's alive. Plants, however, quickly give up this carbon when they die and decompose. But if we can divert the carbon cycle at this key juncture, we could keep the carbon from this biomass from entering the atmosphere in order to begin to rebalance the carbon cycle today, which is very important, because that is when action is needed. We can't make immortal trees yet, but it turns out that we can do the next best thing. And we have known how to do this for a very long time, thousands of years in some cases. When we thermochemically decompose the biomass through a simple and energy-efficient process called pyrolysis, then we can lock up the majority of biomass carbon as a highly recalcitrant substance, which is called biochar or charcoal. Very common substance, or very familiar substance that we all know of. This biochar is 80% carbon, and what's left over after the process is a lattice of this carbon that contains innumerable microscopic cavities that microorganisms love. The process that creates this biochar, or pyrolysis, is also called hydrothermal carbonization, and is itself being developed as a source of energy because it produces such a high quality fuel from a renewable resource. However, we can also utilize this process to make biochar that we can put into the earth in order to sequester the carbon. Because of biochar's ability to promote microorganism growth and the incredible amount of carbon in it, it is a popular soil amendment already. And it is one of the main ingredients, in fact, of terra preta soils found in the Amazonian river basin. Now, researchers think that this terra preta was built up over hundreds of years by the pre-Columbian civilizations that were likely much more populous than we had thought previously. The evidence supports that these sophisticated societies essentially created their own rich soil in order to support their at the time, massive populations. The terra preta is incredibly fertile because it's a mix of not only biochar, but animal dung, fish scraps, food scraps, fish bones, rather, and sundry other compostables. And in some cases, reaches 6 feet in depth. Most of their land surfaces in this area are covered with a red, acidic soil that is not nearly as fertile. And so this terra preta only exists in patches throughout the Amazon, or throughout this particular area, and has been found to be an incredibly fertile soil. The civilization that once thrived there likely depended on this dark black soil to support the population. So today, as our global population continues to increase, the need for arable land also increases. Not to mention the burgeoning demand for organically grown food, which is the perfect counterpart for this biochar enhanced compost. And it has the benefit of locking carbon into the soil for thousands of years in a self-sustaining cycle that promotes many benefits other than the carbon locking itself. In order to utilize biochar as a carbon sequestration tool, the substance must be mixed with other organic material, or compost, and applied to the soil in vast quantities. This healthy soil will retain water much more efficiently, it'll have better structure, it will promote the creation of carbon-rich humus, and it will also facilitate the growth of carbon-hungry fungi. Recent research has shown that underground fungal growth, in particular, already sinks more carbon than trees. The main problem with many carbon mitigation solutions is the scale of the problem. To add unneeded insult to injury, solutions are often expensive, complex, or depend on forcing organizations to lower their emissions. Which, by the way, if we lowered emissions all the way down to zero, we would still have to sequester carbon from the atmosphere to return to a normal, stable carbon cycle. So we must sequester carbon, and this is one way we can do that. And the benefits of it are that it is essentially a ubiquitous material. Biomass is available everywhere, and it's usually free. Unlike the production of so many other goods in our economic system, the more biochar enhanced compost we make and use, the better it is for the planet. However, in order for the biochar enhanced compost to be truly sustainable, the product must be sourced locally, used waste biomass, and sold for profit. In order to meet these parameters that I just outlined, we should set up a well-marketed set of compost hubs within urban and rural communities and allow open access to drop-in compostable materials at this hub. It is important to emphasize here that any biomass should be collected locally and contain only waste. Again, growing biomass to turn it into biochar is not sustainable and adds cost to what must be a money-making proposition. There are also many possibilities for developing a pickup service to feed more carbon into the system that's created. The possibilities for developing a pickup service might be particularly lucrative in communities that don't have municipal waste management. So both kitchen and yard scraps waste could be voluntarily dropped off for processing at this central point. There would also be a large component of large yard waste collection from local curbsides. Much of the woody yard waste would be processed into biochar and eventually mixed with the compost that is also created on site. The high amount of carbon in the compost will ensure little odor production during the composting process, and the biochar will ensure the compost creates the carbon sink. Creating the biochar is also a carbon neutral process, important. And this efficiency is somewhere around the neighborhood of 90%, and it depends on the configuration of the pyrolysis stove, because the gas from the pyrolyzing biomass is continually burned to fuel more of the same. So it's a closed cycle that uses its own created gases to fuel the process. There's also a significant amount of heat produced in this process. So this heat can be used on-site or off-site to power equipment, or it can be stored later for use. One of the most exciting developments in recent news is the announcement of the Tesla battery, which could very easily be used within this application, especially given the size of the hub and its ability to deliver a sort of distributed electrical capacity. So, in other words, there's going to be an energy positive process taking place here, and we can get that energy from the process and offset other energy use. Any material not suitable for composting can be sent to something called an anaerobic digester, and this is another well-proven technology. But some of the things that are that should not be included in the compost can be readily accepted by an anaerobic digester. So if we use this alongside of composting, biomass, and alongside the biochar, it can add a very helpful supplement. This anaerobic digester, it produces a high methane fuel called biogas. It produces CO2 and even more compost. The biogas could be sold and would therefore offset non-renewable fuels. Creating biogas in digesters also diverts methane, which is a powerful greenhouse gas in and of itself. It can divert those emissions, and it can prevent even more atmospheric pollution. The valuable CO2 should be diverted solely to highly efficient greenhouses, where it can be kept in the tightest space possible and can be used to directly grow biomass, and hopefully that biomass will then be composted and turned back into soil and kept tightly within the carbon cycle, and instead of letting it become emissions in the atmosphere. The scale and immediacy of action needed is quite daunting. So we should take the task on part by part in order to slog through to a solution. And I think this is a very exciting potential solution, in that it can be distributed and done in small parts. By selling this enhanced compost, we can fund carbon sequestration independently through market forces. We can also reduce the need for petroleum-based fertilizers that are leaching through land and into our waterways, which is in itself a huge problem. And it would also create jobs that are impossible to outsource. Thank you for listening.